The main objective of the Black Hole Orbit Lab was to find the mass of a black hole with regard to a star in orbital motion using predetermined position data and Newton's gravitational force law, shown here, along with the gravitational constant g, which is shown here. The black hole's mass was the main result of this lab was that the black hole's mass was found to be 3.38 into 10 to the power 31 kilograms. All the variables within the formula shown above are obtained using given position data, which is used to calculate velocities. Using these calculated velocities, momentum is found and then broken into parallel and perpendicular components in order to find the total net force. All this is represented in a computational model. Python is then used to evaluate the magnitude of the position squared, since the position of the black hole and position of the star are already given. Now, let's refer back to the code. And we know that we need to input some initial conditions that were provided, and this includes the time step, the star's mass, and the position of the black hole, which are all shown here. Also, at this point of the code, this line here, instructs Python to extract the position data from the star data.csv file, which was downloaded from WebAssign. In the first while loop, the velocities, shown here, the velocities are calculated, and Python calculates the velocity of a star on its trajectory orbiting the black hole. And this is the second while loop that shows the steps from which momentum, denoted as p, both initial and final, were calculated using velocity initial and final data. Using the initial and final velocity and momentum data, the changes or delta p and delta v were then found. Okay, now to explain some physics models relating to this lab. When the net force of an object in curvilinear motion can be broken down into parallel and perpendicular components. And so dp dt is defined as delta p over delta t, which is shown here in the formula. And F net is equal to dp dt. Then dp dt parallel is calculated. So this equation here, this component shown here is the parallel component because the change of the magnitude of momentum is taken rather than the direction of the momentum. And so due to the parallel component of an object, an object can either speed up or slow down. However, the perpendicular component only affects the direction the object moves in. And this is the perpendicular component. Now, going back to our code. To find our dp dt, parallel p hat was found, and then multiplied with the change in magnitude with respect to time. Next, to find dp dt perpendicular, we already have dp dt as well as dp dt parallel, and so we merely subtract dp dt parallel from dp dt to obtain the dp dt perpendicular, which is all shown here. Okay, and then dp dt perpendicular is equal to F net perpendicular. And we use these simple concepts because dp dt is equal to dp dt parallel plus dp dt perpendicular. Finally, in the print statement right here, I specifically asked Python to print out the magnitude of the perpendicular and parallel net forces. And using these two, when these two are printed out, they add up to the total magnitude of the overall net force. I also asked to print the mass of the black hole. And Python generates the mass of the black hole using two important lines of code, which are shown right here. In the second line, the magnitude of the net force was found. It also shows the star position minus the position of the black hole squared. Here, the mass of the star is also present. Now here's a run of my code. As you can see, the black sphere represents the black hole, the black arrow represents the parallel force, and the blue arrow represents the perpendicular force. The yellow arrow represents the F net gravitational force towards the black hole and always points towards the black hole as the parallel and perpendicular components add up to the net force. The mass of this black hole turns out to be 3.38 into 10 to the power 31 kilograms, which is shown here. So moving on to the what if questions. The first question is a question asks for the difference between F net dp dt and their components when we say they're equal to each other according to the momentum principle. The answer is that dp dt equals F net is derived from the momentum principle, and dp dt can be calculated from observed position data. However, F net is the force causing the observed motion and can't be measured directly, so it is different because F net is something qualitative while dp dt is something quantitative. The second question provides a scenario where the black hole was replaced with another at the same position, and the question is whether the mass of the new black hole would be different from the original. The answer is that it would not, because nothing has changed besides the black hole, and the positions as well as velocity and momentum data are all the same for the star orbiting. This means that the total net force will also be the same, and so the new black hole will have the same mass as the previous one. Thank you.